Hello, and welcome to this introduction to UML, the Unified Modeling Language. My name is Thomas Judén, and I'm a senior consultant in embedded systems right here in Stockholm, Sweden. The goal of this introduction is not to teach you everything about UML, but simply to give you a first insight into what UML is, and if it could be something for you and your organization. This presentation is just the first in a series of presentations about UML. If you have any questions, please get in touch or watch the upcoming presentations. So, let's dive right in. So, what is UML? Just as the name says, it's a modeling language. And it's a modeling language foremost for software systems. It can be used for systems engineering also, with an extension called SysML, but today I am only going to talk about how it can be used for modeling software systems. UML is a visual modeling language, and what I mean with that is that you're working with different types of diagrams. You can do this either on just the whiteboard or in a modeling program specialized for UML. I'll get back to a few of those tools at the end of this presentation. In the UML standard, there are 14 different types of diagrams specified, and each of them tries to capture a different facet of a software system. Today I'm going to introduce to you 3 of these different diagrams to give you a feel for what can be done with UML. Many of today's programming languages are object-oriented programming languages, and so is UML. UML can definitely also be used to model non-object-oriented systems, but you do get more mileage out of it if your software system is also object-oriented. Now that we basically know what UML is, the next question is, what can it be used for? I'd say that the most common way to use UML is when designing systems and before you start hacking code. If you are in a large organization and you have different systems departments from the development departments, the systems departments would draw up some UML diagrams showing the use cases of the whole system and the deployment of different subsystems and software components. They may also specify the protocols between subsystems. Getting over to the engineers doing the actual implementation, they would break down these UML diagrams into smaller parts and add detail down to the class and object level of the design before starting to write code. If you're really serious about using a UML, you can even generate the actual code from the UML diagrams themselves. The benefits here are that the design and the implementation are always in sync, and by increasing this abstraction level, you can potentially become more efficient. Every software designer knows that their system needs to be documented in the end, but even in the most structured organizations, the state of the documentation is most often too little and too late. If you have designed your system in UML, you already have a high-level visual description of your system. Add some clarifying text, and you're done. If you haven't designed your system in UML from the beginning, or if you have a large amount of legacy code, there are tools for you to reverse engineer your code into UML diagrams. Or if you're generating your documentation from code comments in, for example, the Doxygen style, there are plugins to define UML diagrams directly in the comments. Now over to the different diagram types. As I said before, UML consists of 14 different diagrams. I'm not going to explain all of them now, but don't worry. I'm going to go through most of the diagrams deeply in the upcoming presentations. But let's look a bit closer at the different groups of diagrams. First of all, we can see that the UML diagrams are divided into 2 different main groups. On the left we have the structure diagrams. These diagrams are very static, and most of them show the different components building up the systems and how they relate to each other. The components I'm talking about could, for example, be nodes, executables, classes, or objects. On the right, we have the behavior diagrams. They show more what is happening during runtime. They basically show the logic as it is implemented and how the system reacts to stimuli. A subgroup of the behavior diagrams are the interaction diagrams, while the other behavior diagrams show the behavior within a component. Interaction diagrams show behavior between components. They could, for example, describe how the client and server react to each other's inputs over an interface. I'm going to go through one diagram each from these three groups, and I'm going to start with a structure diagram, the class diagram. So here we have the class diagram. For this example, I have prepared a class diagram over a car and some of its components. Each box here is a class. In object-oriented programming, a class is an encapsulation of data and functions in that data. And this is exactly what we have here also. First we have the class name, in this case car. Below that we have the attribute, that's UML speak for member variables. In this case we have the attribute gas that represents how much gas there is in the car. Then below that we have the operations. That's what what's in other languages are called methods or member functions. Here we have fill for filling up the car with gas and start for starting the car. You see that small lock in the gas attribute? That shows that the attribute is private. This means then that the attribute isn't accessible from outside the class. The operations in this class don't have the lock and therefore are public. You can also often see a plus sign for the public attributes or operations and a minus sign for those that are private. Then we have these lines between the classes that are all over the place. These are associations. An association signifies a relationship between two classes. Here, for example, we have an association between the engine and the transmission. The number at each end is the multiplicity. With the left-hand number, we say that each transmission knows about one engine, and with the right-hand number, we say that each engine knows about one transmission. A general association is a very fuzzy way to describe a relationship. There are a few more specific associations, one of which is called a composition, or composition aggregation. This signifies that if an object of an owning class is destroyed, so is the owned class. This filled in diamonds at the car class shows that it is composed of one engine, one transmission, and 4 wheels. If the car is destroyed, so is the engine, the transmission, and the wheels. Now, we only have one more thing to explain here, and that's the arrows here at the bottom. These are called generalizations, which is the same thing as what is usually called inheritance in a programming language. That is to say that one class is a type of another class. In this case, we have a transmission as a base class. This base class is a generalization of the derived classes for manual transmission and automatic transmission. Or we could say that the manual and automatic transmission classes are inheriting from the transmission class. In this example, I've shown the differences between the manual and automatic transmission classes in that the shift operation is public in the manual class and private in the automatic class. As you can see, it's very easy to get an overview of a class diagram and how the different classes are related to each other. For a developer, it is also very much faster to hash out class diagrams on a whiteboard than it is to write a number of class declarations in code. So when starting developing a new feature, I'd highly recommend starting with drawing up a class diagram to get a feeling for the structure. So that was the class diagram. Now let's move directly over to a behavior diagram, the state machine. A state machine is a classical way to describe a logical structure, and a great way to code in a way that doesn't end up looking like spaghetti. Instead of having lots of variables defining different cases, we specify states we move between. Depending on the state we are in, we get different behavior. So here we have a prototype of a state machine for a safe. A safe can have 2 basic states. It can either be locked or it can be open. On the state we have a lock. This safe has a numeric pad and then an unlock button. The idea is that you first punch in your code and then press the unlock button. To model that, we can in the state machine have nested states within other states. So within the state safe closed, we have 2 other states, lock idle and waiting for more digits. To get between the different states, we have transitions. All transitions have a trigger. That is the event that forces the transition to be evaluated. But then it also has a guard. This is an extra statement that needs to be true for the transition to be carried through. It could be that a local variable needs to have a certain value, for example. So if the trigger has happened and the guard is true, then you move from one state to another. A transition can, as an extra bonus, also have side effects. For example, it could send a message to another system. We call this side effect an action. So, let's try to see if we can move through the state machine. Each state machine has a starting point. This is signified as the transition coming from a round ring. We see that at the top of the screen here. So we start in this state safe closed. Then, because this state has nested states, we also have a nested starting point. We see that starting point going into the lock idle state. From the lock state, we have lock idle state, we only have one outgoing transition, and that is triggered by a digit being entered into the numpad. But a lock that only requires a password of 1 digit is a pretty poor lock, so that transition takes us into a state where we are waiting for more digits. In this state, you also see the text digit entered. This is an indication that we, within this state, also are waiting for the trigger digit entered. But that if this trigger comes, it does not change the state, we only handle it. We call this a do action. There are also two more special internal triggers called onEntry and onExit, which are executed when entering a state and exiting a state, but I'll talk more about those in another presentation. Anyway, we stay in the waiting for more digit state until somebody presses the open button. And here you see that depending on the value of the guard, in this case, if the correct code was entered or not, we follow two different transitions. If the incorrect code was entered, we are back in the lock idle state. If instead the correct code was entered, we perform the action lock disengaged and move out of our nested state and into the safe open state. There is only one way out of the safe open state, and that is by pressing the close button under the condition that the door is closed. This then performs the action of engaging in the lock, which takes us back to the lock idle state, since that is the initial state in safe closed. And that's it with the state machines. State machines with a lot of states going back and forth can look daunting, but I can promise you, they are a hell of a lot more difficult to follow in code. So, as you saw, the state machine diagram didn't show any structure at all. You couldn't see where the triggers came from, and you couldn't see who the actions affected. To model interactions between different objects, we must of course go down to the interaction diagrams. The most common of these diagrams is the sequence diagram. Let's head down that rabbit hole. So, what do we see here? At the top we have a number of boxes. These represent objects. Well, all of them, except the leftmost one here, called env for environment. It's basically a pseudo-object representing all external actors outside of our system. Anyway, to connect it with the class diagrams, think of these objects as specific instances of the classes you model there. In the example here, I tried to show a simple model view controller pattern. It could, for example, be a website with a web page as a view, a web server as a controller, and a SQL database as a model. The environment would then be the user interacting with the view. And in this case, it would be a user trying to create a new account. When doing a layer implementation of this, of course, the controller, for example, would be split in a number of classes. So don't see it just as a class in a programming language. In this case, it is a subsystem we're talking about. Below each object, we see what is called a lifeline. This is a representation of the life of the object. Time here is moving from top to bottom. Then, between the lifelines, we have the interactions. We call them messages. It is possible to differentiate between the synchronous messages and asynchronous messages, but I haven't done it here. I'll go more into that in a later presentation. So, first we see the user entering her username, and after that her password. This doesn't trigger any action from the view. It's not until she clicks OK that the viewer reacts by sending then a message to the controller. In the create user request message, we can see that it attaches two attributes, the username and the password. Then we have this funny looking box. This is a reference to another sequence. It might not look like much, but it is one of the great additions to UML 2.0. Before then, you couldn't reference other sequences, and this limited the size and complexity of systems you could model with sequence diagrams severely. Now we can build up hierarchies or reusable sequence diagrams that goes deeper and deeper into the system and shows progressively more detail. In this case, the sequence we are having a reference to is a sequence to validate the user and password. For example, it could check that the username is free and that the password has a high enough complexity. Then we have another of these funny looking boxes. This is also new for UML 2.0 and it's called a combined fragment. There are 12 different combined fragments, and the one you see here is called alt for alternative. This is basically a UML version of an if-else-if statement. As you can see, the box is divided by a dashed line. At the top of each of the boxes, you see something you should recognize from the state machine diagram, and that's the guard within the braces. If the guard is true, this section is run. So in this case, if the user name and the password is valid, we run the top part. This would then lead to that the controller creates a user in the model before returning an OK message to the view. If the input wasn't valid, we can see in the second part of the combined fragment that not OK was returned instead. Let us take a moment and compare the sequence diagram to the state machine diagram. When would you use which diagram? Of course, if you have multiple components, the sequence diagram is usually a better fit. But that is not enough of a reason sometimes. As you hear from the name, sequence diagrams are not that good at showing control flows that never end. So if you have some kind of interface or protocol where there is a lot of logic, which makes you go back and forth, but really doesn't have a well-defined finishing point, I definitely go for state machines. You would then of course need to model one state machine for each object, but it could be worth it. Another option though is also to divide the protocol into parts that are more linear and model each of these parts as their own sequence diagrams. I think this is a really good way to do it. For example, in a protocol you might have a handshaking procedure in the beginning followed with different reactions depending on what the higher layer wants, something out in the environment. Then I would model the handshaking procedure as one sequence diagram and the other parts as other sequence diagrams. As a bonus, the tester could very easily write a test case out of each of these different sequence diagrams straight off. This makes it extremely easy to verify that all the required functionality is implemented. Just run the test for the sequences that are defined. It's that easy. And with that we wrap up the sequence diagram part. So now I've showed you one structure diagram, one behavior diagram, and one interaction diagram. With just knowing these three diagram types, you get very far. I would really recommend you to learn these three diagram types first and start to use them in your work before you move on to learn more types. You really shouldn't use more diagrams than necessary either. For example, the communication diagram is basically a sequence diagram where it's easier to see relationships between objects, but without the possibility to show logic. It definitely has its uses, but if nobody else in your organization knows how to read it, you shouldn't really use it. So, first, make sure everybody in your organization knows the basics of UML and can use that. Then, later on, you can start to pull in other diagram types as the maturity level in the organization increases. When it comes to tools, there really are a multitude. The tool I always recommend you to start with is the whiteboard. Don't let the effort of learning a software tool stand in your way of learning UML. Just two designers in a conference room with a whiteboard hashing out designs is very hard to beat. But then, when you feel ready to take the next step, you really should start using a tool to be able to at least save away your diagrams for documentation. There are a number of different diagramming tools that can do a UML right out of the box or with some extra plugins. Visio is one of those, for example. There you can download free UML stencils online. Remember though that with Visio, it's only visual. It doesn't understand the context of what you're drawing, and you can totally forget about connecting different models with each other or generating code. Microsoft isn't pushing for Visio as a UML tool either. Instead, they are pushing software designers to use the diagramming tools in Visual Studio. They only support 5 of the most common UML diagram types, but for most purposes that will take you quite far. Strangely enough though, state diagram is not one of the types they support. Anyway, IBM though is a very serious play in the UML field with their Rational Rhapsody product. Depending on what you want to do, you can spend anything from a few $100s to well over $10,000 for a license if you want to do code generation and reverse engineering. If you're only interested in creating UML diagrams though, they do have a free version called Rational Modeler. That's what I have been using to create the models in this presentation. I do have a bit of a crush on IBM Rational's suite of software, with the Rational Purifier being a favorite of mine for finding memory leaks. And if you are from an enterprise and where tool costs aren't as big an issue as the highest quality and the best support, I can very much recommend all their products. If you do both care about code generation, reverse engineering, and your financial sanity, I can highly recommend Spark Systems Enterprise Architect though. Their tool costs a few $100 and has a great reputation for being good value for the money. And with that, we are pretty much done. I hope you have gotten a better understanding for what UML is and what it can do for you. If you have any questions, please leave them in the comments below and I'll do my best to answer you. If you're interested in me holding a course at your premises for your colleagues, to kickstart your organization, just get in touch with me directly. Otherwise, subscribe and you'll be the first to know when my next presentation is out.